Namaste students. Today we will learn the last topic of the nitrogen family, that is the oxoacids of the phosphorus. In our previous video we have studied that what is the meaning of the oxoacid. Oxoacid is a substance which contain hydrogen which is attached with the oxygen. So oxoacid is a substance which contains the replaceable hydrogen attached with the oxygen. So in this video we will study the preparation and the structures of the 9 oxoacids of phosphorus. So without any delay, let's get started. So today our topic is oxoacids of phosphorus. So the first oxoacid of phosphorus is H3PO2. The first oxoacid of phosphorus is H3PO2, and the name of this oxoacid of phosphorus is Hypophosphorous acid. It is Hypophosphorous acid. Now first of all we will talk about the preparation of hypophosphorous acid. Now we will prepare hypophosphorous acid by treating white phosphorus with aqueous solution of barium hydroxide. When we treat white phosphorus with aqueous solution of barium hydroxide solution, then we get phosphine and a byproduct, that is BaH2PO2 whole twice. Then this BaH2PO2 whole twice on treating with H2SO4, it gives BaSO4 plus H3PO2. So in this way we can prepare hypophosphorous acid. So hypophosphorous acid is prepared by treating white phosphorus with the aqueous solution of barium hydroxide, and then the byproduct which we get from this reaction on treating that byproduct with the H2SO4, we get BaSO4 and H3PO2. Now if we talk about the structure of H3PO2, its structure is P double bond O, OH, H and H. So in this structure, it is clear that though we have 3 hydrogen, but the replaceable hydrogen is only 1, and that hydrogen is attached with the oxygen. So the replaceable hydrogen is this one, and this is attached with OH. That's why it is an oxoacid. And because of the presence of only 1 replaceable hydrogen, it is monobasic. It is monobasic, means its basicity is 1. I hope you all know about basicity, means the number of the replaceable hydrogen ion in an acid is known as its basicity. So though the number of hydrogen are 3 in this, but the replaceable hydrogen is only 1, that's why it is monobasic, its basicity is 1. Next, second one, we will talk about H3PO3. In second, we will talk about H3PO3, and that H3PO3 is known as orthophosphorous acid. That is known as orthophosphorous acid. Now first of all, we will talk about the preparation of the orthophosphorous acid, which is also known as phosphorus acid. So either phosphorus acid or orthophosphorous acid, both are same thing. Now, if we talk about the preparation of the orthophosphorus acid, we can prepare orthophosphorus acid by 2 methods. First, by hydrolysis of P4O6. This we have studied in our previous video, that P4O6 on hydrolysis gives H3PO3. And second, PCl3 on hydrolysis gives H3PO3 plus HCl. So we can prepare orthophosphorus acid either by the hydrolysis of P4O6 or by the hydrolysis of PCl3. Now if we talk about the structure of orthophosphorus acid, its structure becomes P double bond O, single bond OH, single bond OH and single bond H. So it becomes H3PO3, and due to the presence of 2 replaceable hydrogen, due to the presence of two replaceable hydrogen which are attached with the oxygen. This is the oxoacid of the phosphorus and its basicity is 2. Therefore, it is dibasic. Therefore, it is dibasic. So, by these two reactions, we can prepare orthophosphorus acid, and by structure, we get to know that it is a dibasic acid. Now, next, third, we will talk about the third oxoacid of phosphorus, that is H3PO4, and H3PO4 is known as orthophosphoric acid. Orthophosphoric acid. Now, orthophosphoric acid is prepared by two methods. Orthophosphoric acid, we can prepare orthophosphoric acid by two methods. First method is P4O10 undergo hydrolysis to form H3PO4. P4O10 undergoes hydrolysis to form H3PO4, and PCl5 reacts with water to form POCl3 plus HCl, and then this POCl3 reacts with water to form H3PO4 plus HCl. So the final product is H3PO4. Though the reaction completed in two steps, but the final product is H3PO4. So we can prepare H3PO4 either by this method or by this method. And if we draw the structure of H3PO4, it is P, double bond O, single bond O, OH, single bond OH, and single bond OH. So, due to the presence of three replaceable hydrogen, which are attached with the oxygen, it is an oxoacid, and due to the presence of three replaceable hydrogen atom, it is tribasic. Next, fourth, if I talk about, that is H3PO5. Next is H3PO5, which is known as peroxomonophosphoric acid. Peroxomonophosphoric acid. Now, it is prepared by reacting P4O10 with 30% of aqueous hydrogen peroxide solution. By treating P4O10 with 30% of aqueous peroxide solution, we get H3PO5. So because of the when it reacts with, means when P4 reacts with the 30% aqueous solution of hydrogen peroxide, then we get peroxomonosulfuric acid. And why it is known as peroxomonosulfuric acid? Because of its structure. So its structure becomes P double bond O, single bond OH, single bond OH, single bond OH. So because of the presence of this linkage, it is peroxo means peroxy. Peroxomono, because only one linkage is there, so peroxomonophosphoric acid. And why it is phosphoric acid? Because its basicity is 3. So it is a tribasic oxoacid. So we can prepare H3PO5, that is peroxomonophosphoric acid, by treating P4O10 with 30% of the hydrogen peroxide solution, aqueous solution. So these are 4. Now we have to study 5 more. So the 5th one. Now next we will talk about the 5th one. I hope the 4 are clear to you and their structure, and through structure we can easily calculate their basicity. Now we will talk about the 5th one. 5th one is H4P2O5. 5th one is H4P2O5, that is, which is also known as pyrophosphoric acid. Pyrophosphorus acid. It is pyrophosphorus acid. It is pyrophosphorus acid. Now, how we can prepare pyrophosphorus acid? We can prepare pyrophosphorus acid with the help of the phosphorus acid only. With the help of the phosphorus acid. H3PO3 on reacting with PCl3. H3PO3 on reacting with PCl3, it gives H4P2O5 plus HC. So by treating H3PO3 with PCl3, we get H4P2O5 means pyrophosphorus acid and along with HCl. Now, if I talk about the structure of the pyrophosphorus acid, its structure is PO, P, double bond O, double bond O. Now, how many oxygen are left? 2. So, H, OH, OH, H. So, this is the structure of the pyrophosphorus acid. And its basicity, if I talk about its basicity is 2. So, it is dibasic. It is dibasic. And dibasic is our phosphorus acid. So, it is pyro. Why it is pyro? Because of the presence of this linkage, POP linkage. Because of the presence of POP linkage, it is pyro. And phosphorus, why? Because of its basicity, that is 2. So, pyrophosphorus acid, and we can prepare pyrophosphorus acid by treating H3PO3 with PCl3. Now, next, 6, we will talk about H4P2O6. H4P2O6, that is known as hypophosphoric acid. That is known as hypophosphoric acid. Now, this hypophosphoric acid is prepared by treating white phosphorus with aqueous solution of NaOCl. This hypophosphoric acid is prepared by treating white phosphorus with aqueous solution of NaOCl. We get H4P2O6 plus NaC. So by this reaction, we will get pyrophosphoric acid, that is H4P2O6. Now, if we talk about the structure of hypophosphoric acid, so if we talk about the structure of the hypophosphoric acid, it is P, double bond O, OH, H, OH, OH. This. Clear? OH, 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 OH. And if I talk about its basicity, and if I talk about its basicity, so it is tetrabasic. It is tetrabasic. This one is tetrabasic. So, when white phosphorus reacts with aqueous solution of NaCl, then we get H4P2O6 and along with NaCl. And this oxo acid is tetrabasic because it has 4 replaceable hydrogen ions, 4 replaceable hydrogen atoms. Now, next we will talk about the 7th one, that is H4P2O7. Next one is H4P2O7, and this is known as pyrophosphoric acid. This is known as pyrophosphoric acid, and it is prepared by the dehydration of the phosphoric acid. It is prepared by the dehydration of the phosphoric acid. So, our phosphoric acid is H3PO4. Our phosphoric acid is H3PO4. On heating H3PO4, it undergoes hydrolysis. And here I will take 2 molecules of H3PO4. On heating, it undergoes hydrolysis to form H4P2O7. H4P2O7. So, when we heat phosphoric acid, when we heat phosphoric acid, it undergoes dehydration, and due to dehydration, it forms H4P2O7. And because it is pyro, so there should be this linkage, there should be this linkage. So the structure becomes P, O, P, double bond O, like this. POP, double bond O. Now here OH, OH, OH and OH. So it becomes H4, P2 and O. 1, 2, 3, 4, 5, 6 and 7. So it again becomes tetrabasic. 1, 2, 3, 4. Tetrabasic, and due to the presence of POP linkage, it is pyrophosphoric acid. Now next, 8th, we'll talk about H4P2O8. Next is H4P2O8, which is also known as peroxo diphosphoric acid. Peroxo diphosphoric acid, and it is prepared by the electrolysis of a mixture of KF. It is prepared by the electrolysis of a mixture of KF and K2HPO4. It is prepared by the electrolysis of a mixture of KF and K2HPO4, and by the electrolysis of these two solutions, means the mixture of these two compounds, we get H4P2O8. And if we draw the structure of H4P2O8, we get which linkage? That is the OXO linkage. So the structure is like this. P O O P, double bond O, double bond O. How many oxygen are left? 4 oxygen are left. So OH, OH, OH and OH. So this is the structure of the peroxo diphosphoric acid, and because of the presence of 4 replaceable hydroxyl group, it is tetrabasic. This one is also tetrabasic. Now next, the ninth one is known as metaphosphoric acid. Metaphosphoric acid, that is HPO3. Now this exists in two forms. One is the cyclotri metaphosphoric acid, and second one is the linear polymetaphosphoric acid. The first one is the cyclotri. Cyclotri means it is in the cyclic form, and 3 means 3. So it exists in two forms. First one is HPO3 whole thrice, and second one is HPO3 whole N. This one is known as cyclotri metaphosphoric acid, and this one is known as linear polymetaphosphoric acid. Now if we want to prepare this, we can prepare this with the help of H3PO3. On heating H3PO3 with bromine in a steel tube, we can prepare this, that is the cyclotri metaphosphoric acid. We can prepare this by heating H3PO3 with Br2. This one, H3PO3 with Br2 in a sealed tube. Then we get HPO3 whole thrice plus HBr. Now if I draw the structure of these two, if I draw the structure of cyclotri metaphosphoric acid, it is like this. P double bond O, single bond P, single bond O, P, O, O. It is like this. And here it is double bond O, OH, double bond O, OH. So here it is single bond, double bond O, OH. Like this. So it is H3PO3, HPO3 whole thrice, and because of the presence of 3 replaceable hydrogen atom, it is tribasic. This one is tribasic. So this is the structure of cyclotri. This is the structure of cyclotri metaphosphoric acid. And if we draw the structure of the linear metaphosphoric acid, if we draw the structure of linear metaphosphoric acid, it is like this. P, then single bond, OH, O, P, here it is double bond O, then again here it comes OH, here it comes so OH. So due to the presence of only one OH group, this one is monobasic. So cyclotri metaphosphoric acid is tribasic, whereas the linear polyphosphoric acid, linear polymetaphosphoric acid is monobasic. So these are the oxoacids of the phosphorus, in which we have hydrogen, replaceable hydrogen, which is attached with the oxygen, and we have calculated the basicity of each oxoacid with the help of the structure. Studied about 9 oxoacids of the phosphorus, and the last one is the metaphosphoric acid, in which we have studied that metaphosphoric acid is present in 2 forms, either cyclotriphosphoric acid or linear polyphosphoric acid. Now the polyphosphates are used as a water softener in detergent. There is a use of polyphosphates. There is a use of polyphosphate, and what is that use? That polyphosphates are used. These are used as a water softener, in detergents. Water softener in detergents. But the use of polyphosphate in the detergent as a water softener is banned in USA. Means the use of the polyphosphate has been banned in USA. And why it is banned? Because it decreases the oxygen level of the water. It decreases the oxygen level of the water, and because of this, it has been banned in the USA. But if it is there in your question paper that what is the use of polyphosphate, so polyphosphate are used as a water softener in the detergents. Now one thing you have noticed, that in all the oxoacids there should be a P double bond O. There should be a P double bond O. Means no one oxoacid is without P double bond O bond. So there should be at least one P double O bond in every oxoacid of phosphorus. Next, the pH bond. Means if suppose we have pH bond in the oxophosphorus acid, that oxophosphorus acid acts as a reducing agent. So greater the number of the pH bond, greater is the reducing agent. And if you study all the structure of the oxoacids of phosphorus, the very first structure, that is H3PO2, which is known as hypophosphorus acid, it contains 2 pH group. It contains 2 pH group. So H3PO2 act as a strong reducing agent. H3PO2 act as a strong reducing agent. Why it act as a strong reducing agent? Because of the presence of 2 pH group. Because of the presence of 2 pH group, it acts as a strong reducing agent. And H3PO3 also act as a strong reducing agent, but weaker than that of the H3PO2. So H3PO2 is the strong reducing agent in oxoacids of the phosphorus, while H3PO3 is the weaker reducing agent as compared to the H3PO2. Suppose I have AgNO3. When AgNO3 reacts with H3PO2, then it forms Ag plus H3PO4 plus HNO3. So what it did, it reduces AgNO3 to Ag. It reduces AgNO3 to Ag. Similarly, suppose I have HgCl2 plus H3PO2, then it reduces HgCl2 to Hg plus itself oxidized to H3PO4 plus HCl. So these are the reactions through which we get to know that H3PO2 act as a strong reducing agent. And if we talk about H3PO3, yes, it is also act as a reducing agent because of the presence of one pH group. I hope you are getting my point. H3PO2, the structure is like this. So due to the presence of two pH bond, it acts as a reducing agent, and H3PO3, due to the presence of one pH group, it also acts as a reducing agent, but little bit weaker than this, because in this we have two pH group, in this we have only one pH group. And in this, suppose I have AgNO3 plus H3PO2, then it gives Ag plus H3PO4 plus HNO3. Means the reaction is same, but the extent of reaction is little bit less as compared to the above one, the rate of the reaction. Next, suppose if I have CuSO4 reacts with H3PO2 to form Cu plus H3PO4 plus, not 2 here, it is 3. So plus H2SO4. But if HgCl2 reacts with H3PO3, then it forms Hg2Cl2 plus H3PO4 plus HCl. So these are the reactions through which we get to know that these two acts as a reducing agent. And why these two acts as a reducing agent? Because of the presence of pH group. So if we have pH bond in an oxophosphorus acid, then it acts as a reducing agent. So students, that's all for today. That we have studied the structure, the preparation and the basicity of the different oxoacids and oxoacids of phosphorus. I'll see you in my next video with the new family of the